Well, good morning all, and this morning we are going to be looking at something called the conjugate root theorem. So that's a little term there to impress your friends with. I drop that into casual conversation as often as you can. That will impress everyone. Well, it sounds like you've just been to the dentist. So anyway, conjugate root theorem. We need to start really with the factor theorem. And hopefully you'll remember that the factor theorem works a little bit like this, is that given a function, say f of x, and some factor x minus a, and x minus a is a factor of the function if f of a is equal to 0. In other words, if I shove a into the function and the result is 0, then we know it's a factor, and also that a is a root or a solution. A is a root. There we go. So that's the factor theorem, and it's very useful when we come to factorize long polynomials. It takes some of the heavy work out of it. All right, so let's have a look at an example. And we've got a question. Here's a function. And I've got that function is equal to x squared plus 9. And I want to know, is 3i a root? So before, we've used the factor theorem for polynomials that are real with real solutions. So now we're looking at them with complex solutions. So is it a root? Well, it works the same way. We can test to see if that's a root by substituting 3i into the function. So we go ahead and do that. And I squared is -1 and 3 squared is 9. So I get -9 plus 9, it's equal to 0. Hooray, look at that. We've got a root. In fact, we can carry on and say, well, and this leads really into the conjugate root theorem rather nicely, is that, can you see that this function here is over R? So that function, we talk about that being over R. In other words, it has only got real terms, or terms with real coefficients. And we say, well, where's the other one? Where's the other root? Because it's a quadratic, so we're expecting 2 roots, and 3i is one of the roots. Where's the other root? Well, roots often come in conjugate pairs. In fact, they always come in conjugate pairs when the function is over R, which is the conjugate root theorem. I'm sort of ahead of myself here a little bit, but that's okay. Let's go and put that in and see what we get. So we get -3 squared I plus 9. And what have we got now? Well, 3 squared is still 9, or -3 squared is 9, and I squared is still -1, so I get -9 plus 9 is equal to 0, and there's my other root. So therefore, the roots are 3i and -3i, and that means this whole thing factorizes, which we kind of already know anyway. It factorizes to x minus 3i times x plus 3i. And the reason I say we already know that is this is the sum of 2 squares. So look at that, there's a lot in this lesson already. So we come back to this idea of the sum of 2 squares. Sum of 2 squares factorizes to give us some complex roots, which we've got. Right then. Let's have a go at another example, just again using the factor theorem before we get ahead of ourselves. So let's look at what I've done. One example makes that one example 2, keeping them sequential. And let's go ahead and factorize this thing over here. So factorize, and I've got x cubed minus 5ix squared plus x minus 5i. So we need to go ahead and factorize, or make it a function, keep it official. Right, well, always start with something easy, all right? And let's start with, you could do 1 and -1, but we're just, they would be the usual suspects to start with. So we start with 1 and -1. And well, let's go and do 1, all right? See what happens, all right? So we'll do 1, and we'll see whether we get that equal to 0 or not. So 1 cubed is 1, 1 squared is 1, so I get minus 5i, plus 1, and minus 5i. So you can see that's not equal to 0. In fact, if we add all of that together, I get 2 minus 10i. So it's not 0, therefore 1 is not a root, and x minus 1 is not a factor. And if we try -1, we'll get the same thing. We'll work out that's not going. So once we've dismissed 1 and -1, we'll go ahead and try I and see whether that works. So if I substitute I into this function, that's what I'm doing over here, then I get I cubed minus 5i squared plus I minus 5i. All right, just check that you've substituted correctly. I always like to put little brackets around so that, yeah, it's just a bit of a safeguard to ensure I'm doing everything properly, particularly when it comes to different signs. So I think I've substituted that correctly, so we can go and work that out. I cubed is -i, and I've got another I cubed. So I times I squared is I cubed, which is -i. So that becomes times -5 is positive 5i. And then I've got plus I and minus 5i. Look at that. Cancel, cancel, cancel. 0. And we have found our first root. So therefore, you can see there that therefore x minus I is a factor. So we can go ahead and try -i, because that's the next sort of obvious one to try. Always try the easy ones first. That's why I said try things like 1, -1, I, -i, and you usually get solutions. You're looking over here, that choose a different color. You're looking at that -5i, because that's going to help us to work out what those, potentially what those solutions are. Right? It could be, 1 complex root, it could be 3 complex roots, or some combination. So we'll look, that's what we're looking for. So I and -i, so we'll try -i. So -i cubed minus 5i -i squared plus -i minus 5i. So substitute that in. Well, that gives me I, because -1 cubed is -1, I cubed is -i, gives me I. That still gives me minus, that gives me plus 5i. That's minus I, and that carries through. And look at that, we get the whole thing cancels out again, so that's 0. So the next factor that we have got here is minus I, and therefore x plus I is a factor. Now, really, we're nearly there, because what we're looking for, of course, is that function there. And I've got x plus I, x minus I, and then x minus a, which is the last one. So you can go ahead and keep trying using the factor theorem, and you just keep trying stuff. And if you look there, we should be, I times -i is 1. So it should just be 5i. So a is equal to 5i, all right? Because this multiplies through to give you x plus 1, x minus a, and then 1 times what is equal to 5i. And And we're done. So there it is there. Here's my, I factorized it now. X minus I, X minus 5i. And again, if you try 5i into yeah, you can do that, I'm not going to. But if you factorize, if you put 5i into that, it'll work just fine. So that's that idea. All right, let's look at the conjugate root theorem then. And the conjugate root theorem basically says this: if we've got a polynomial and the polynomial is over R, so there it is there, polynomial over R, and one of the roots is over C, in other words, it's complex, then the other must be its conjugate. There we go, and that's it there. We'll draw a nice box around that, and that's the idea behind the conjugate root theorem. So let's look at an example. What are we up to? 4. What is the polynomial over R, meaning it has no complex coefficients, with roots 3 and 2i? All right, well, I've got one complex root here. So if I go ahead and set that out, therefore I've got f of x, x minus 3. I've got x minus 2i. But if I multiply that out, I'm going to end up with a complex coefficient. You can see there, I get x squared, get minus 2ix, get negative 3x, and I get negative 6i. So there's complex, you know, go ahead and do it, but you can see there I'm going to end up with complex bits. So this is where the conjugate root theorem says if the polynomial is over R, and we know it's over R, then the other root, or the other factor, must be its conjugate. So look at those. I've just added that second, or at least I've added the third factor in there, and it's a conjugate of x minus 2i, x plus 2i. Okay, and we know that conjugate pairs, when we multiply them out, the complex part is eliminated. So let's go ahead and do that, and we'll get that. So we get x squared, and we get plus 4. All right. So you know how to do that. X times x is x squared. You get your negative 2ix and positive 2ix cancelling out, and then negative 2i times 2i is equal to 4. So if we carry on multiplying that out, I get x cubed minus 3x squared plus 4x minus 12. And that is the answer to what we've got. Now, if you look carefully at that, can you see there that all of the coefficients, and just a quick lesson if you've forgotten what a coefficient is, x cubed coefficient is 1, x squared coefficient is negative 3, the x coefficient is 4, and the constant is negative 12. Look, all of those are real. Okay, there are no complex coefficients there, which makes that polynomial over R, and that's why we needed that extra pair. Now let's do one more, and we say, what is the polynomial over C? What about the same thing, but this time over C? So we've got the same roots, all right? So we've still got the roots. What were they? 3 and 2i. Well, if it's over C, then there's multiple options, right? we could add some other ones here because we're not told what kind of polynomial it is, but the simplest polynomial would be a quadratic because we've got two roots and that's all we know. So that's all we've got to go on. So here we go. If it's over C, it's x minus 3, x minus 2i. So our function must just be a quadratic. This one, of course, the one we just did is a cubic. And we just multiply that out. And by the way, this will help us to clearly see too that there's complex parts there. So x cubed minus 2i, x minus 3x, and then plus 6i. And we should do this. Should be x squared minus 2i plus 3x plus 6i. We do just group that that x coefficient together in that way. There we are. That'll do it. We're done.